Welcome to ECE 20002. My name is Art Turlip, and I will be your instructor for this summer session. Um, this is going to be a little bit unique. We're doing all of our stuff online this summer, so a little bit challenging. I'm a current PhD student at Purdue University, former U.S. Air Force science officer. Some of you have jokingly asked, what the heck you're supposed to call me. I used to go by Captain, so you can see that. But Art will do just fine. There's no problem. The goal for this course is for you guys to learn the fundamentals, obviously, since it's fundamentals 2. My background is more in mathematics. I actually have my bachelor's in math and not in electrical engineering. So what I have in deficiencies for electrical components, I hope to make up for in mathematics for you guys, so that you guys have a really strong foundation, really good fundamentals moving forward into your other courses, so that as electrical engineering is mostly math anyway, you guys know what you're doing in those courses come. In particular, a lot of the emphasis I'm going to place will be on things like convolution and transforms, and really getting a good conceptual understanding of what those different spaces and different operations that we apply mean. And when we talk about frequencies and filters, I want you to have a very firm understanding of how we got there mathematically, and then conceptually what is going on at a heuristic level. So I look forward to helping you guys master that kind of material. I know a lot of you are actually coming from 2002 in the spring, and that's okay. Sometimes it takes more than one go around. Sometimes the class isn't necessarily the best fit at the time. We'll put it that way. And and some of you are coming from 2001, and I hope you gain the knowledge that you need to move forward. If not, we're going to review some of those basic concepts. I know math can be a little bit tricky sometimes, so we're going to actually review the ordinary differential equations that you might need. So don't worry about that. And as far as calculus is concerned, we'll kind of walk the dog a little bit on some of them, but there's an expectation that you already have a certain mastery of calculus. With that, we're going to go ahead and jump into sort of my syllabus expectations for the summer, and then we're going to get right into the material with op amps, leading into MOSFETs and how to design op amps, and then that'll be about our first 7 lectures or so will be this bundle of op amps and MOSFETs. After which we'll get into the convolution stuff, Laplace transforms, and all that good stuff. So, okay, let's begin. So I'll be doing all my stuff in GoodNotes here. All right, so that's today. I'm pre-recording this lecture. You may notice that it's being recorded on May 20th at 10:47 a.m. This lecture is intended for June 15th, 2020. All right, so we talked about the ordinary differential equations. We do have a TA for this course, fortunately. That's Xiao Yu. She will be hosting office hours online, probably via WebEx, on Thursdays for sure, from 2 to 4. And that's our local time. And then my office hours will be Tuesday and Wednesday from 2 to 4 as well. Tuesday and Wednesday. All right. MATLAB, we're going to use for some demonstrational purposes. I'm probably not going to have any requirements, since I'm recording this lecture pretty early. That is subject to change, okay? So, may change, okay? But it's pretty unlikely to, because we're already very condensed. So, assigning you guys a project, especially when it's online, is not ideal. Okay, weekly quizzes. These are fixed. These are like little mini exams. It should be about a half an hour long. I figured breaking it up would be better, and then, the whole timed exam thing isn't, you mess up one, you get a couple more shots. So it kind of breaks it up for you. And then it also helps isolate which material you really need to focus on for that final. If you need an exception, I need to know by what is supposed to be tomorrow, June 16th, anytime before June 16th at 2:30, so that I have at least 24 hours to make arrangements for you guys and figure that out. As for the final, it's probably going to be take home. Again, subject to change. I may change my mind on that. But at this time, I plan on giving you guys 24 hours for a take-home final. So it'll be harder, but it'll be more interesting and really push your skills that you acquire in the course. Okay, cheating. I'm only going to go over this once because we're never going to have to talk about it again. So the consequences of cheating at the university are not great. They're pretty crappy. Typically, the first offense isn't as harsh, but I have no patience or tolerance for that. And being a former Air Force officer, I love paperwork. So don't make me do paperwork. You'll regret it. If there's cheating on a mass scale, I will recommend that the whole course just get thrown out and no grades be awarded at all. I can't get tenure or anything, right? I'm not a professor. So I'm just an instructor, and this isn't my full-time gig, right? So I don't really care if we have to chuck out, the baby with the bathwater. Don't make me go there. So that being said, yeah, there's kind of been a history of some issues back in the spring with students cheating. I think that, I'm trying to be fair with you guys in terms of not doing these online proctor services. A lot of the other courses are starting to require these online proctor services, making you install what's basically spyware on your own personal computer. I don't agree with that. I don't think it's necessary, and personally, I wouldn't want that. So I'm not going to make you guys do that. Don't give me a reason to change that, please. So we'll leave it at that. Finally, do not distribute tests, quizzes, etc. online. Not only does this violate our university policies, it violates the copyright laws on the book. And I don't even know what the hell Amazon does when you start to share their materials. It's probably not great. So our book is published through Amazon. So technically, I don't know how that works. Anyway, won't be good if you start copying stuff from the book or the future versions of the book, as the homework will be. Okay, speaking of which, the book is only $40. We're going to follow it very, very closely. Okay, sometimes you may be like, oh, hey, Art's just copying straight out of the thing. Well, yeah, that's because I wrote part of it. So these are like the codified versions of things that I think are really important and what Dr. Tolovich thought was really important. So if it looks like I'm reading out of the book, it's because, that's what we think is important. So it's not going to be a purchase that you're going to regret for sure. And the nice thing about it is that since we're following it so closely, you can take notes directly in it. We left it double spaced just so you have plenty of room in the margins to do whatever you want with it. So please buy the print version so you can doodle, while I'm rambling. It'll be great. Op amp. Da 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 da. It's actually the lesser known Triforce of voltage. The operational amplifier, as it's called, is just another building block for us to use and put into our toolbox. We're going to develop the ability to see what's actually going on inside of the operational amplifier later on in the course. In particular, the next 7 lectures or so are going to be about kind of building that operational amplifier. But for right now, it's just going to be a black box. In particular, a couple of notes about this before we dig in. These DC supply connections aren't really relevant in the ideal case, but functionally, they're there to keep in the back of your head. What does it do? It does it all. It slices, it dices, It computes sums, differences, integration, differentiation, and most importantly, it scales, okay? That's why we call it an amplifier. So we're looking at how much gain we get out of this thing and what kind of operation it applies. Now, some limitations are going to apply, obviously, because components can't do all of this stuff without any kind of restrictions. So we'll explore those later on as we learn what the MOSFETs are doing inside here. All right, little history. These things all used to just be vacuum tubes. The first one was back in 1941. It was a summing amplifier used as an artillery director. And then we have the development of transistors. Transistors and silicon transistors, giving us a commercial op amp in the early 50s. Then we have high-speed, low-input, current MOSFET designs that eventually led to the 1980s MOSFETs that got replaced inside of our op amps. So in short, our transistor development goes hand in hand with our op amp development. And that's pretty much it. I got most of the stuff from Wikipedia, so if you're interested in the history of this stuff, which I am, I encourage you to go look it up and see the progression of these things. This is pretty fascinating, seeing how we go from these big bulky objects to being able to compute certain things like integration, for example, just from a little tiny piece of hardware, which is just incredible. Okay, so off to the left here, we have a picture that I took from our book of the simple dependent source model. And the most important takeaway from this is that the ideal op amp is useful in circuit design because it is a virtual short that exists between the two terminals, meaning that our current at both of the nodes is equal to 0, and that's going to come in very handy when we start to do some problems here and all of the examples we have for our common op amp configurations. And we have a 0 difference between our voltages at the two nodes. All right, let's dissect one of the diagrams that we have for our common op amp configurations. Let me show you some of the different configurations available to us. The name of the game here is going to be figure out what Vout is based on our inputs and based on our resistor values and the given configuration. So we're going to derive a number of these today, and you're going to be expected to be able to use them and derive them yourself on homework problems and subsequently on exams and tests. Looking at this diagram here, off to the right, wanted to point out what different things are. We have our input voltages. We also have our input resistors. And then we have two feed-forward resistors, although in truth, we call, here we go, forward resistor. In truth, we actually call this one the feedback resistor, or it's the feedback loop is what it really is. And this feedback loop goes from our output terminal right here, and it feeds back into, for all of our common op amp configurations, back into this negative terminal. And when we refer to these, we actually call this the inverting terminal and the cleverly named non-inverting terminal, or node. Okay, so now that we kind of have all these parts figured out, oh, and one other thing, sorry, feed forward lead. That's right here. Okay. So for this particular problem, we're going to be measuring V out as the difference between V3 and V4. Okay, it's measuring that voltage potential. In order to do this, we're going to use an old favorite, Kcl. Right? Our good old current law. And we're going to do that at our two nodes, A and B. All right, so at A, what we have is the following. We have a voltage drop, right? As we come into our node at A. We also have no current flowing down into that inverting terminal. And then when we look at the current to the right, we know that that's just going to be determined by our V3 and our RF, our feedback resistor. So we set this up as follows. We have what I'll call IN plus we'll call it IF plus I minus. This all has to sum up to 0, right? Well, we know that this guy goes to 0, or is 0, by definition. And we know that this is determined by that nice voltage drop we have there. So this is going to be V1 minus VA over our resistance that it dropped over. So using Ohm's law, we're able to derive this pretty easily. Remember, V equals IR. If you don't know that, you might want to pause the video, go back to your old 20,001 stuff and like really review for a while. Okay, and then we have, on the other hand, V3 minus VA over RF. And that's all going to just sum up to 0. Okay, so I'm actually going to write this a little bit differently, just to make it clear. So what we want to solve for here is V3, because at the end of the day, oops. And why don't we do another color here for the for V4 as well. We'll do purple. So we'll do V4 there. So our two unknowns that we're trying to solve for here are V3 and V4. And ultimately what we want is V out, okay? So given all these other things over here in black, right, we can solve for V3. So we do a little bit of algebra, and we end up with the following. So we move this guy over to the other side, subtract it over, and then multiply both sides by RF, and then add VA to both sides. The result is going to be that V3 is equal to RF over R in times VA minus V1. Oh, I hate it when instructors do this. Hang on. I know how to do this. I'll fix it. Yep. Aha. Nice. Actually, I just want the other part. That should give me enough room. Okay. Perfect. Now we got room. Plus VA. I don't like writing stuff on multiple lines. Okay, so now we have V3 isolated. So what we need to solve for next is our V4. So similarly, we look at, let me just cut this off real quick so I got a little bit of extra space. Look at node B. And at node B, we have a similar situation. We have the voltage drop across Rn, but this time it's coming from V2. So when we look at it, and this guy again is 0, by the way. When we look at it, we have V2 minus VB whatever that may be, over Rn plus V4 minus VB over RF. And again, we have this invisible plus 0 from the non-inverting terminal. There's no current coming to or from that direction. The sum must be equal to 0. Again, we do the same algebraic manipulation to arrive at V4 is equal to RF over Rn VB minus V2 plus VB. All right, well, that's dandy and all, but we need one more piece of information, and that is that VA is equal to VB. The op-amp requires that A and B are equal potential. So we actually can kind of take this just as a given that the fact that these two voltages are the same. So we can rewrite this guy, and actually we'll just do an equal sign. Rewrite this guy as RF over Rn times VA minus V2 plus VA. And fortunately, we also picked our two input resistors to be the same, and our two forward resistors, one of them being the feedback, to be the same as well. So when we put these two equations together, we're going to find that they mesh rather nicely. So if we take V3 minus V4, we end up with the following. The VAs are going to cancel throughout the entire equation, and you can probably see that from here. So we end up with RF over Rn times V, make sure I get the order right, V2 minus V1, okay? And you could actually write this another way that I kind of prefer, which is, and I know it's kind of a silly thing, but it makes sense since a lot of these other forms have a minus sign in the front. I like to write it this way. Okay, there we are. So minus RF over Rn, V1 minus V2. Okay, and that's exactly what we have in the final result as well. So what does this get us? Why do we care? Well, what we've done is we've effectively taken the difference between these two terminals for voltage, and we've transformed it or amplified it by a gain factor to acquire a new voltage potential between these two terminals. That's fantastic. We actually just use this device to change how much voltage we have between two nodes, or the difference between two nodes. So, very useful tool starting out. All right, let's see what else we can do. Let's do something a little bit more simple for this one. In this diagram, the non-inverting terminal is connected to the ground, and we're pretty much left with what we had on top from the previous configuration. So we really don't have too much to solve here. We actually just have the following. We again start with IN, right, plus IF plus I minus equal to 0. This guy is equal to 0 by definition. IN is conveniently, once again, just VN over RN plus this guy, no change here, right? It's just V out over, and note here that our V out in this circumstance is just measured with respect to our ground. So we don't really have to worry about, we're not taking a differential in this situation. So we have this over RF, and that's equal to 0. We rearrange our terms to isolate V out, and we find that V out is equal to minus RF over Rn times Vn. That's it. We've solved it. Took us 3 lines. Not too bad. So you guys should be able to do this. If you understand what's going on at this node, in terms of KCl, you're in great shape. All right, let's do another one here. The integrating amplifier is a little bit different. In this instance, our feedback is a capacitor. And interestingly enough, the integrating amplifier has the feedback as a capacitor, but the differentiating amplifier has a capacitor in the input, and it keeps a resistor right there. So you can see the duality at play here between integration and differentiation. Very, very easy to switch between these two. And their forms are very similar too. So that it just makes sense, right? It just makes some mathematical sense. So let's go ahead and try to prove that identity that we have on our cheat sheet there. Again, we're just going to use some good old KCl. But we have, and I always like writing these guys in pairs, right? We have a pair of equations that we love to use when we get to capacitors and inductors. In this instance, we got our capacitor equation. Our current is equal to our capacitance times our voltage differential, or the change in voltage with respect to time. So when we look at IF, let's go and write this out formally first. All right, there's our Kcl equation. This guy don't change. If it ain't broke, don't fix it, right? There we go. Now IF in this case is equal to C times, and in this case it's actually CF. CF times dV dt. And in this situation, our voltage drop is going to be V out once again. So that's it. Now we just solve. So what we have here is we want to solve for V out, or dV out dt actually. And then we'll kind of work from there to show you why this is the integrating. In any case, we have minus 1 over Rn CF V in, right? That's equal to d dt of V out. That should be pretty clear. If we integrate both sides with respect to t, it becomes pretty clear why this is called the integrating amplifier. That's because V out is equal to an integral. Now this is a little loosey-goosey because this is a, you haven't defined your limits or anything on your integral. So, but for all intents and purposes here, you can see that we've effectively integrated our input voltage to produce our output voltage. So that's a very useful tool for us. All right, let's go ahead and do the summing amplifier as well, since we have quite a bit of time left on this lecture. And then I want to talk to you guys a little bit about the book and some of the content that's in there, and then we'll take a quick sneak peek at the lecture for next time as well. This lecture is kind of short, being the first one. I think that's okay. The other ones will be longer and a lot more dense. All right, so let's go ahead and build this summing amplifier. So for the summing amplifier, you're going to have three inputs, right? You got V1, V2, and the cleverly named V3. And instead of calling it RN1 and all this, the book calls it RN1. I'm just going to call it R1. You got R2 and R3. Okay? And we're going to put these all together so that they're in parallel. And then they come in here and they go to the inverting terminal. Let's see. Yeah, it's a little crooked, but that's okay. slightly different. Okay. And then this guy just goes to ground, and this is our V out. And we call this again RF. Okay. So again, we're going to be looking at this special node right here, where everything comes together. And in this circumstance, you can collapse this bit of wire here and just say, hey, these all kind of come together. You could redraw this almost as, all of these wires all coming together at the same point, right? We can simplify our diagram a little bit. So when we write our Kcl equation, we're going to have I'm just going to call it I1 plus I2 plus I3. So our current coming from all three of our sources there, here, here, and here, plus whatever is going out the other way over to this side. So we'll call it IF. And then, of course, we have our our I minus, which is still not doing anything. Makes our life easy, though, for calculating this. Okay, these guys are all pretty straightforward. Since we have V1 and we have R1, we can just write the following. And here we're going to use V out once again and RF. Okay? So that equals 0. Now we want to isolate V out. Pretty easy. Just move everything over to the right-hand side and multiply by RF. So V out is equal to RF times, excuse me, we'll put a minus sign right there. V1 over R1 plus V2 over R2, 2 plus V3 over R3. Let me make sure I didn't make a typo back here again. No, we're good. Okay. All right. I've recorded this lecture more times than I would care to admit, and every time I get a handful of typos, and it's driving me nuts. So I want to make sure. All right. So here we go. We have all of our stuff here, all of our ducks in a row. Okay, a few other quick notes about how we're solving and setting up this equation. So you'll recall back when we were looking at the differential amplifier, they were looking at the voltage drop V1 minus VA. And then we exploited the fact that VA must be equal to VB. Remember, we talked about that over here. That kind of by definition, these two are equivalent to each other. Sorry. So one thing that we could do here is confirm our differential amplifier real quick by confirm our inverting amplifier by simplifying our differential amplifier equation. So if we set a bunch of this stuff equal to 0, i.e. we ground it out, do we get the same result? And the answer is yes. So if we look here, if we set V2 equal to equal to 0, we end up with our inverting amplifier here. So our equations and our methodology is consistent. And again, with the summing amplifier over here, which we just did, wanted to make that note because we've sort of been running along with this assumption that all of these guys here are just their input values on those terminals there, and that there's no difference there, right? And that's because we have our ground right here, and these two potentials are roughly equivalent to each other, so we're able to exploit that assumption. Okay, let's see here. I've got a few more minutes of time, so one other thing to add in post here. I totally forgot to mention this when I was recording originally, so I'm going to go ahead and just add it now. But when we talk about op amps, one of the most important things is the amp part, the amplification. So we need to discuss that for a second. All right, so when we are dealing with op amps, we talk about AVI. And this is our voltage gain. And we define AVI as being equal to the ratio between V out and VI, or generally VN. And I want to take a second to review our common op amp configurations and look at those gains, because those are going to be super important for us moving forward. And you can see why I rewrote this originally to be V1 minus V2. But you can see here our gain is actually just a ratio of RF to RN. Okay, and we have that same ratio here. Then we have other versions of that throughout. So like when we're looking at the summing amplifier, it's sort of spread across all of our different inputs. So the amount of gain that you get per each input is related to the reciprocal of the resistor value that goes in, which makes sense, times the feedback resistor value. So yeah, that's the takeaway I want you guys to see here. So for a lot of these cases, let's just kind of write out one of these cases here. Take the simple one, because I think that's kind of the best. We'll take the inverting amplifier, and I just want to really spell this out. So V out over VN, so we had V out was equal to RF over RN minus VN. Okay, we rearrange our terms here to look more like this. And we end up with V out over VN is equal to minus RF over RN for the inverting amplifier case. And that's just for example. So you can always solve for this gain once you have these equations, right? Because we have this sort of built-in ratio between V out and V in. So it's a really important thing that I needed to add in. Otherwise, you've missed like what the chapter was about. So, all right, back to the lecture. We've done 4 different examples here. I'm going to go ahead and open up the book for you guys and show you, if you haven't purchased it already, what exactly is in there and why it might be helpful for you. So here are all the sections that we're going to cover. Right now we're talking about the ideal operational amplifier, and some of the examples I did in the class here today are in the book. I will probably provide a lot of additional examples, or as we move along, I might jump out of the book and do some of the homework problems. Even though the solutions are posted, I find it very helpful to sometimes have a live tutor for learning how to do those. So as a student, I can appreciate seeing homework examples done, even if the solutions are already there. So we'll probably do a little bit of that in class, and not necessarily follow the book verbatim every single lecture. Although there are a lot of good examples and stuff in here. Okay, so like I said, we're gonna talk about ODEs. So you can see here that we're going to review all the good stuff about ODEs, just how to generally solve them. Then we're going to apply that to circuits. Later on, this is kind of my bread and butter, is the convolution and Laplace transform, all that good stuff. In here, we'll probably do a lot of examples. The convolution section, the reason I mention it so much is that seems to be a sticking point for a lot of students in the past, and it seems to be a difficult subject for them to master. So I want to make sure that you guys walk away able to do this in your sleep. We have Laplace transforms, and then we start to get into frequency responses and filtering and all kinds of fun stuff. That's where it really gets fun. And that about does it. So here's the general format and layout of things. You can see that this really follows along pretty tightly with how I covered the lecture today, which is not going to be uncommon. Walks through derivations pretty frequently. Dr. Tolovich did a really good job putting his notes together, so that's kind of what this is a compendium of all of his notes over the years, which is great. It's like the best way to make a book like this. And then I've added a couple touches here and there. And then it's got a lot of very useful tables in a lot of these. For example, when we get to MOSFETs, you can see this is a nice little handy table. Useful equation charts, like here. So you see a lot of this kind of stuff in there that you'd get in a normal textbook, but it will be within the context of what we're going to cover in class, exactly. So there won't be any mystery like, hey, what part of the textbook should I use? All of it. So that makes it nice. All right. Let's go ahead and take a real quick look at the lecture for next time, because we have just a little bit of time left over. So field effect transistor devices, in particular, metal oxide semiconductor field effect transistor devices. All right, it's another kind of FET, right? Yeah? No? All right. I can't hear you guys laughing from here, so I'm going to just assume that you guys are loving all of my little references and nerdology, and unless I hear otherwise. So in the meantime, you'll just have to deal with it, because I'm going to pre-record most of these. So I guess you're stuck with me regardless. Okay, so here we go. I guess you could drop the course. All right, so what we're going to cover in this chapter next time is the how a MOSFET operates, and we're going to look at 4 different modes. In particular, I'm going to focus on the enhancement mode and channel, which you should be familiar with from 20,001, and then we're going to dig into depletion mode and what that means, and what it means for the equations as well. For next time, I highly recommend that you read or review chapters 10 through 3 of your EE Fundamentals 1 textbook, especially 13. So chapter 13, in case you don't recall, looks something like this. I've already doodled on it. Fantastic. Okay, let's erase all my doodles and I'll redoodle on it. Okay. So in chapter 13, he lays out exactly what these guys look like at a structural level. So we have our metal, right? Our oxide, our semiconductor, MOS, right? Field effect transistor. So you apply a voltage to this gate right here, and what you end up doing is creating a channel between these two, and it allows conduction between the drain and the source. All right, and for our purposes, we're always going to write ID, our current, as running down, so that you can always follow along pretty easily. Okay, all of these are going to do that. And we kind of have all the electrons and the holes and the different configurations. Switch which ones are which. We're going to talk about depletion mode, and all those have is like this extra buffer doping around all of our terminals and stuff. Okay, so I think that'll cover it for today. I'll sign off with you guys here so you can see my pretty face before we go. Oops. All right. Okay. So I've enjoyed trying to make this lecture today. It's been kind of difficult. I'm not gonna lie. I even lost my hat, I guess, in the middle of this. It's been kind of chaotic. So please, I ask you to just bear with me as we work through this, and I'm learning with you guys a little bit here too. So if I make any mistakes, please feel free to correct me, and we'll get it sorted out. I also want to encourage you guys to have an open and academic discussion on the Brightspace forums. So hopefully I'll have those up and running by the time the class starts. But, if you guys are having trouble with the homework, I feel like, using each other as resources is very valuable. And I don't like assigning group projects or anything like that. But, if you got a question, throw it up there, and I'm probably going to leave it unless you email me directly and let other people try to take a crack at it. I can neither confirm nor deny whether or not that'll help, push you over the tipping point if you're kind of between grades. If I see that you're active in the forums and helping people, or even just asking questions, that's just as important as knowing the answer. So if you guys do that, you'll be in really good shape for the future, because realistically, in industry, you guys aren't going to have to memorize a lot of stuff. You're going to have your computers open. You're going to have 55 windows open, and you can look up all those equations and everything. But what you really need to learn that you don't learn as much in college, and especially at a time like this, is how to work with other people, asking questions and answering questions. So I think it's important for you guys to do that, and I'm not going to have some compulsory way of doing it, but, feel free to engage, and you should. And try to enjoy the class a little bit. I hope it's fun, and I hope you enjoy it moving forward. All right, that's enough rambling from me. Our next lecture will be a lot less of me talking about nonsense, because I won't have time. There's a lot of stuff to cover in lecture 2. So thank you all very much, and look forward to working with you.